So we have been estimating confidence interval for the mean. Well, confidence interval for various population parameters. And we haven't done many. So last time which we were discussing was this case. I think we called it case 2, where you are estimating confidence interval for the mean. For the mean, and you know, given that the population is normal. So that's all you know, that the population is normal. If the population is normal, then the only two parameters you need if you want to define the characteristics of the population are only its mean and its standard deviation. Completely characterize the distribution of the population. And this thing you want to get at, but you don't know, you have no information about this either. So how would you do it? And we said that we can have defined this parameter. So something which looks very close to a standard normal. Where this is the sample mean, this is the population mean, and this is the sample standard deviation. So with this new variable, it looks pretty much like the normal distribution. It's a bit fatter at the tails and centered again at 0 for any one of these. And we also have from this relation from here we have minus mu, and you want to look for some value of this t, some critical value to be critical. So this is also symmetric. T's distribution is symmetric. So some critical value of t, so that if you around this, you compute this probability, that the probability of t being within this range is equal to your specified value beta. Then to find this T critical, you have that probability of t n minus 1 being greater than this T critical is alpha by 2, where alpha is 1 minus beta. So this purple total area is alpha, which is 1 minus beta. And if you want to just count this, if you want to get it this number, you can get it by this thing. So then this critical thing we were writing as greater than T alpha by 2. And this same thing can be written that this variable is less than alpha by 2 with a probability 1 minus alpha by 2. Because if this is the probability for this T to be greater than T critical, this purple one, then the rest would be just 1 minus this. And what does it give us from this equation? What is this critical value of? So you have some value for your x mean when it is equal to mu plus margin of error. Then from this equation you get that margin of error is this T critical time this. So this would just be simply under root 10. And this margin of error would then be used to compute the upper confidence level, which is mu plus margin of error, and lower confidence level, which is mu minus margin of error. And then your confidence interval is simply this interval. So this is the summary of what will be done. Every time you do almost exactly the same thing, except that sometimes you are using a different probability distribution. So let's see this in action. Let me do a couple of examples. So suppose this is a problem from the book, problem 7.29. So suppose there's a car company and they want to estimate that what is the average number of days that their cars are out of operation. Well, let's say for maintenance or something. So obviously it's important thing for them to know. And they know all the assumption is that this distribution is normal. What distribution? How many days cars are out for maintenance? Well, it will be a random variable, some for more days, some for less days, and the assumption is that it's going to be a normal distribution about that how many number of days they are out of operation. That's all you are assuming. So assuming this, they want to find the mean number of days, and they do a sampling, and they pick a sample of 9 cars, and they find that the number of days are these. So from this data, they can first of all find the sample mean, and they can find the sample standard deviation, These things will be needed to compute the margin of error, but they will also need to compute this critical value of the t variable, and they want to estimate the mean. Obviously, you cannot give an exact number. Estimate and give a confidence interval. And when you say a confidence interval, then you have to say how much confidence. So let's say we need it for with 90% confidence that within this interval lies the mean average number of days that the cars are out of operation. So we have to compute this, and we have to compute this from this data, and we have to then compute. So what would this mean? That means that beta is 0.9, alpha is then 1 minus beta, it's 1 minus 0.9, it's 0.1. And this t, you have to compute. This t involves this number, n. So given, depending on what is the sample size, the distribution is slightly different. So over here, you have to put n minus 1, and this value alpha by 2. So which becomes for us t8 with a 0.05. Now, I want to do this computation today in SPSS. So let's see how would, yeah.
Sir, tn minus 1 का logic क्या है?
Logic इसका आपको याद होगा कि we did this कि ये जो हमने variable define किया ना, ये जो variable define किया, आपको याद होगा कि we had this variable chi square n minus 1, which we had said that this variable gives us the, if I define like this, then this distribution is the distribution for the standard deviation or the variance of sample, not of the sample mean, sample variance. So that is given by this, and that depends on the number of variables. So what you are doing is, since you do not know the population variance, so you are replacing the population variance by this variable. So when you put this in your standard formula, your formula, you are defining a variable which looks like the standard normal, which usually you define this way, where this is the sample, the variation, the standard deviation of the sample mean, which is equal to under root n. So over here, you place this variable. And when you replace this variable, then you just divide by things and you compute a new random variable. So since this variable has the dependence on the sample size, so this new variable which you create also has a dependence on the sample size.
Okay, sir. Thank you.
So this is our data, and we want to compute these things. So this is SPSS window. Let me This is some other data which I'll use later. So I can just open a new data, and then you have these columns. So if you have a sample, you can just start typing in those numbers. So this is the entry for which I had in the samples. So I'm just putting in 21, 22, 8, 17, 19, 14, and then 19 again. I had a sample of size 9. So you have put this sample here, and it just, when you put it in, it automatically gives it a name variable 0001. So if you want, you can change this name. So over here, you can go to variable view and give some name over here. Let's say days. And I want to compute those some basic things, like I want it's the mean of this sample mean, and the sample variance, because I need those things in my formulas. So what you can do is you can go to analyze, and over here you can use many different options. You can go to descriptive statistics, and you can go to either frequencies or just descriptives. So for example, if I just go to descriptives, this is the variable which I am doing this analysis for. So I put it over here and I click on options, and it gives me different options that what I want to look at. So I don't need all these things. All I want to compute is the mean and standard deviation. So I continue and I just press on OK. And this is the output. It tells me that the mean is 16.222 and standard deviation is 4.79. And remember, in SPSS as well, when you compute the standard deviation or the variance using just this command, it does the sample standard deviation and sample variance with a division of n minus 1. So if you're doing it for sample, you don't have to correct with anything. So let's put it in a new data sheet. So I had this number 16.222 and 4.79. So I can go to variable view and call this the mean and call this the standard deviation. Now these are my mean and standard deviations which I have. And now I want to compute this over here. I want to compute this critical value of t, for which I have this value. And how did I define it? I can define it through a cumulative probability that t is less than this value, this critical value, so that the probability would be, remember, it is this thing which is 0.05. So if I'm doing the cumulative distribution, then this would be 0.95. This is just 1 minus alpha by 2. So 0.95. So how do I compute it? Again, I can go to this, for example, this window. And this is computed to, you go to transform and compute variable. Now, when you do compute variable, you can store it in some new column. So let's call it T critical. Give it a new name of whatever you will compute. And over here, you have to write a formula. But in this case, we are not going to write a formula ourselves because we are computing some critical value to a probability distribution, and SPSS, and just like Excel as well, has a whole number of important probability distributions stored in them, and they can do computation for us. What we are doing is finding a critical value, giving a certain probability. So this is called given a certain cumulative probability, because this is how I'm writing t less than a certain value. So it's a cumulative probability up till this point over here. So you go to here. This is called cumulative distribution, but in this time it would be the inverse cumulative distribution. Inverse distribution for t. And it gives you a description over here that you give it a certain probability. You want to find the critical value of the t variable for certain probability and a certain number, which degree of freedom means that n minus 1 which went over there. So if you click it twice over here, it just brings in here. And for us, the probability is 0.95 because that's the 1 minus alpha over 2. And the degrees of freedom for us were 8. N was 9, so n minus 1 is 8. And I store it in this new variable t critical. And you just press OK. And it appears over here. So I found this, and then I have to use this formula to compute margin of error. T critical times S over under root n. I can do that directly in SPSS again. Again, I go to transform, compute variable, and this time I want to call it margin of error. And this is not what I'm computing, so I erase it. And I'm just doing a simple multiplication so that you can do, because in this formula, you need t critical and multiply it with the standard deviation. So you just click on it, it comes over here, multiplied with the standard deviation because I had stored it in this variable. And you want to divide it by under root 9, which is 3. So let me just directly put divided by 3. And it will be stored in this margin of error. So it comes over here. So the margin of error is 2.97. And then I can compute the upper confidence level. Let me just do it over here. UCL. And that's just mean plus margin of error. (19.19). Similarly, I can compute the lower confidence level. That's just mean minus margin of error. So it's 13.25 and 19.19. So I have computed that the confidence of interval with 90% confidence based on my sample is, let's see, what was it? 13.25 to 19.19.
Sir?
Wait. So somewhere here between 13 days and 19 days is your mean number of days that the cars are out. And this you can say with 90% confidence. That means if you again make pick up a sample and compute an interval around it, you repeat it many times, then 90% of those intervals will contain the true value of your population mean. Yeah, what's the question?
Sir, I think 0.95 for T critical is 1.645.
1.645. How did you get it?
Sir, at 0.95 probability,
One. Why are you saying it? We can calculate it again. So transform compute variable. Inverse numeric returns the value of a student's t distribution with specified degrees of freedom df, for which the cumulative probability is equal to this probability. So our probability, let's put it in t critical 2, and our probability, combined probability is 0.95, because I'm doing it with confidence interval of 90. So beta is 0.9, alpha is 0.1, alpha by 2 is 0.05. So in the cumulative distribution, I have to put in 1 minus alpha over 2. So I put in 0.95, and the degrees of freedom are 8, 1 less than the sample size. And it's 1.86. I don't know, how did you compute 1.96? Probably you are computing using the normal distribution, standard normal. It's not the standard normal. That's the point. When you don't know the standard deviation of the population, then you're not using the standard normal to estimate it. Then you are using this student's t variable, because to define the standard normal variable, you have to divide it by, you have to use the standard deviation of the population, which you are not sure, which you are estimating using your sample. But you know that when you estimate the standard deviation of the population using your sample, then from the sample, you will always get a different number. So it becomes a random variable itself. So that randomness also feeds into the new variable, t variable you are creating, and its distribution becomes slightly different from normal distribution. It will become normal distribution if your sample size is very big. Why? Because as your sample size grows, your standard deviation is becoming narrower and narrower, and then you can more accurately estimate the standard deviation without much randomness using your sample. And then it goes towards it starts becoming looking more and more like normal distribution. But in general, for small enough sample sizes, one has to use this t variable, which is also called the student's t variable. Is this clear now?
yes, sir.
Okay, so let's do another example. So I'll next time show you how to open files in SPSS, but I just fed in this data, this that you have a truck company and you want to estimate what is the average consumption of fuel for your fleet, and all you're assuming. So if you don't know anything, many times you can assume that your population probably is going to be the normal distribution, unless you have strong reasons to believe otherwise. And you can do some tests as well to check how close to normal it is, that we will learn later. But right now, let's just assume that the population consumption is normally distributed and you don't know anything else. So you picked a sample of size 24, and these are the consumptions of those 24 trucks, fuel consumption per gallon. I mean, this is the, you can say that this is the miles covered per gallon for these trucks. So you want to, again, estimate a confidence interval, let's say. Example, given the data, the sample of 24 trucks and their consumption, find a confidence interval for the fleet's mean consumption with a confidence of 95%, let's say. So your t variable is 23, and the critical value you're finding, beta is 0.95, alpha is 0.05, alpha by 2 is 0.025. And the cumulative probability you have to find is that t is less than this critical value. The number which comes over here is actually 0.975, because 0.975 plus 0.025 is equal to 1. So this thing you have to put it in, but we also need the population and the sample mean and the sample standard deviation. So it's just a little bit more practice. You have this data written in this column consumption. So the nice thing is that you can just start typing in the data in a column, and then you can go to variable view, and there are different things you can do to it. We don't need to be concerned with other things at the moment. You can just give it a name over here, which I have already given. Then you go to analyze descriptives. You need mean and standard deviation. And wait. So this is the consumption, that's the variable. 24 is the number in your sample size. This is the mean and this is the standard deviation. So let me open a new data file, because if I store it in here, it just puts values in all of these. You can do that, but it won't look very nice. It's a new data file. And mean is 18.679. and standard deviation is 1.695. Okay, so now here we encountered a problem that it's only retaining it up to 2 decimal, and you can see why is that so, because over here one of the properties which is defined over here, that the decimal is defined only up to 2 decimal points. This variable is defined up to 2 decimal points, so you can increase it. Let me put it 4. Similarly, and give it a name actually. And you can straight away define a new variable and give it 4 decimals. Go back to data view and put in the value of standard deviation, which is 1.695. Now, I want to compute that inverse probability. So you go again, let's write a target variable, which is again T critical. And you go to inverse distribution functions and inverse T. Probability is 0.975. Degrees of freedoms are 23. So the T critical is 2.47. And I can finish my calculation of margin of error by again going here. So margin of error is just equal to T critical. Here is the formula. T critical times S over under root n. Sorry. So I have T critical times standard deviation divided by square root of 24. So square root, you can also look up here. If you go to arithmetic functions, there are many functions given here. And one of them is square root. And for us, the number was 24. So the margin of error is 0.72. It is not much, and the reason is that we have a large sample size. And from here, you can just compute the confidence interval by adding this margin of error to your mean. So that's this example. Well, let me complete it. 18.679, 18.67, let's keep it to 2 decimal, 18.68 plus 0.72. 19.4. So confidence interval with 95% confidence is 18 Not this one. Let me close this file. Let me close this too. Yeah, 18.68 is the mean, and margin of error is 0.72. Minus 0.72. That's the interval. Now, let's do another example. I won't use any data. Let me just use some numbers. Let's say. So a school wants to estimate that what is the average salary of the graduates 5 years after their graduation. So what they do, they send out a survey to 25 randomly chosen graduates, is the sample size. And from there, they compute the mean, sample mean, to be dollars. And they also compute that the sample standard deviation is 4780. So remember, to compute this, you just need the sample. You don't need to know anything about the population. And again, assuming that the population, the salaries are distributed normally in the population. Yeah, Alizan, you have a question.
Sir, so अब Z value use होगी, right?
Z वाली यूज नहीं होगी क्योंकि इन सब में वी आर अज्यूमिंग कि पॉपुलेशन नॉर्मल है, तो पॉपुलेशन नॉर्मल कहने से जी यूज नहीं होगा. अगर पॉपुलेशन नॉर्मल के साथ यू नो व्हाट इज द स्टैंडर्ड डिविएशन ऑफ द पॉपुलेशन, देन जी यूज होगा. Here we don't know what is the standard deviation of the population. This is the standard deviation of sample, not the standard deviation of the sample mean. Standard deviation of the sample, आपने एक sample pick किया और उन number से you whatever standard deviation you compute is the sample standard deviation. It's that number. You don't know what is the standard deviation of the population, only of your sample which you picked up. So based on this, you want to say that with 90% confidence level, what is the mean salary? So 90% means alpha is 0.1, alpha by 2 is 0.05, 1 minus alpha over 2 is 0.95. Here is some critical value. T in this case is going to be 24, and here is some critical value. कहाँ पे है? So that this is alpha by 2, this area, because it's symmetric. ये भी alpha by 2 है, so ये becomes beta, which is your desired thing, 0.9. But to get to here, you use all this cumulative probability. The probability for T to be less than this number is equal to what? 1 minus this number. So is equal to 0.95. So again, you can do it on SPSS. Let me just in this file compute a new, because I just have to compute one number. Compute variable, and that variable is gonna give me the T critical. So let's call it T critical 2 because critical is already there. And again, I have to go to inverse distribution. Inverse T 0.95 and 24. So it's 1.71. Let me write this in the notes. So T24 0.05 is 1.71. And margin of error is 1.71 into this number S 4780 divided by square root of the sample size was 25. So I can just do it on the calculator. Wait, I'll come back to you. Divided by 5. So the margin of error is 1634. And the interval then just becomes the mean, which is 42740. 42740 plus 1634. And lower confidence level is 42740 minus 1634. So 42740 plus 1634. So 44374 and minus 1634 minus 1634, 41,106. So you're 90% sure that the mean lies somewhere here. Gives you a pretty good idea. This n-1, I said it many times. That's just how you do it. That's just how this distribution is defined. It's defined with respect to your sample size. I mean, why do we do it? Just because I explained in the beginning, we are not deriving any of this stuff. It's just because the sample distribution itself is a random variable, and that random variable depends on the sample size. Now we can move on to some other cases, some other kind of calculations. So let's say this would be case 3. This time you are giving confidence interval estimation for population proportion. You want to make estimate, you have some variable which is just the proportion, yes or no answers, and you pick a sample, you compute that proportion in the sample, and based on that you want to make a statement about the population. So over here, what you need to assume for the population, pretty much nothing in this case. All you need is large enough sample size. So essentially, what you need to have is that if P is the population proportion, then and N is your sample size, then N P into 1 minus P, if this is greater than 5, then you can pretty much do this procedure. And it's again based on what we have already learned. So remember, we learned that if I compute the population, the proportion, sample proportion, then this is obviously a random variable, but we found that its mean value is equal to the population proportion. This is just the statement that this is unbiased, and its standard deviation is this. And for large enough sample size, well, again, this condition, this sample proportion is actually normally distributed. So this all we have done. So based on this, we can use, based on this, we can define the standard normal variable. Dividing it out by its standard deviation so that it becomes the standard deviation of 1. Now here what you do is, if the sample size is large enough, again that condition, if that is satisfied, you can replace this thing by the sample proportions. Now everything is in terms of sample, and again this for Z, given your confidence level beta, you compute this value of alpha by 2, so that probability of Z being greater than Z alpha by 2 is equal to alpha by 2, or probability of Z being less than Z alpha by 2 is equal to 1 minus alpha over 2. So once you have this critical value, then from this formula, you can see that with this critical value, when I'll multiply this 2 over there, this is the difference. And for this critical value, this would be equal to the margin of error. Because this p hat is by definition, you found it by having it displaced to margin of error from its mean value. And what margin of error? Given this probability. Exactly the same logic as we developed for the mean when we were computing the mean, estimating the mean. This displacement is what you are looking for, and you put in here critical value of the p of the proportion variable, which is just this population mean plus the margin of error. So the population mean cancels and you get margin of error equal to this. So we can again look at some example. So suppose some airline, they want to estimate that how many of their flights get cancelled or delayed, let's say delayed, and they pick a sample of 246 flights from different airports, and in this sample they find that 14 are delayed. So suppose they want to find what is the proportion of on-time flights. Now, in this sample, it's easy. It's just a simple matter of this computation. So on times are 246 minus 14. So that's 232 over 246, which gives me 232 divided by 246, 0.943. But this is the proportion of the sample. They want to have an idea about the proportion of the whole operation over the years or over this year or whatever. So that is different, going to be different from this. This is just a point estimate. So with a certain confidence level, let's say they want to say 98% confidence level, just for a change. What is the population proportion? So this time you are just computing a normal variable. And since beta is 0.98, alpha is 0.02, alpha by 2 is 0.01. So you have to compute that critical value of the z variable, standard normal variable, so that its cumulative probability is equal to 0.99. Again, I can go here. Today I'm just doing these things with the SPSS. Transform compute variable. Let's give it a name. Z critical. And again, I have to compute critical variables. So I have to go to the inverse distributions. So I go to this inverse and I'm looking for inverse distribution of the normal. So it tells you that in the first place, put in the probabilities you want to have for the cumulative probability. and we want to have a cumulative probability of 0.99. And then it asks for mean and standard deviation. But remember, we are now dealing with the standard normal. We are dealing with the z variable. So for us, this is just 0 and this is just 1. So Z critical is 2.33. And then to compute the margin of error, you have 2.33 times proportion, which was 0.943, 1 minus 0.943, and divided by square root of 9, square root of n, which is square root of how many? 246. That's the sample size. I can do it on the calculator. Let's do it just on SPSS. Would be slightly easier. So transform compute variable. Let's call it margin of error 2. And if you look over here, well, I can just put in number. Let's do this time like this, 2.33. And then arithmetic function, square root. I have to put in a multiplication. Square root of what? Square root of 0.943 multiplied by 1 minus 0.943 divided by 246. And you can see that there's a bracket outside the square root. So this is the square root of this whole number. The star is used for multiplication and this dash is just for division. So I can just do okay. And margin of error is 0.03. Probably it gave me this number because I hadn't fixed these variables. They were like having, I can check. Its decimals are only up to 2. So if I increase the decimal, it gives me a better idea, 0.034. So that means the proportion of population is between 0.943 plus 0.034 is between 0.977 minus 0.034 minus 0.034, 0.909. Or you can, some people write it like this. So this was our mean value, 0.943, and then you say plus or minus 0.034 with 99% confidence level. So any question about this? No. Let's move on to the next case. The next case is slightly different, slightly complicated, because we are gonna look for the variance, or we're gonna estimate the variance of the population. So even if you assume that the population is normally distributed, so far we have been getting what is the mean of that normal distribution. But that's not the only interesting question. You can ask the second question as well. You want to know that how spread out the population is. So for that, you will need the variance, or you will need to estimate the variance or standard deviation of the population. And again, you're doing it with one sample, so you will only be able to give an interval that it lies within this interval with a certain confidence level. But that thing, because we know that when we estimate the variance, when we compute the sample variance, we will be trying to compute it using the sample variance. The sample variance is distribution is given by the chi-square, which is not a symmetric distribution. So that means the upper confidence level and lower confidence level will not be symmetrically distributed in this fashion around your sample variance. It will be slightly different. So I think let's stop here and discuss that next time, because we won't be able to complete it this in the next 4 or 5 minutes. We can do instead, we can do some more examples of what we have done so far. Or let's do this thing. Let's do another application. So, well, okay. Yeah, let's do this. So suppose you want to, let me pick some example. So suppose you are given, you pick a sample and your sample size is 350 and your sample proportion turns out to be 0.3, and you want to say, you want to put a confidence interval with 0.9 with 99% confidence. Well, this was not 99. I think we assumed 98. This time we want to do 99. So alpha is 0.01. Alpha by 2 is 0.005. And the critical value Z is less than this. That probability is 0.995. And when we do that, compute variable, inverse normal. Let's just store it in this one. Well, what the heck? Let's compute a new one. Z critical 2, and we need 0.995. It's a standard normal. It didn't come up. What went wrong? We did something wrong here. Let's do it again. Uh, 0.995. Oh, it's log normal. We are using the wrong function. We have to pick IDF normal. 0.995, 0, 1. So it's 2.58. And then all you need to do to compute the margin of error is 2.58 proportion 1 minus proportion divided by 350. So 0.3 times 0.7 divided by 350, square root of this, 0.3 times 0.7 divided by 350, and its square root, and multiplying it with 2.58. So margin of error is 0.063. So it would be around something like that. So let's stop here. Is there any question? Okay, let me stop here.